Find all positive integers n such that there exists a unique integer a in this range between 0 and n factorial with the following property shown here. N factorial divides a to the power of n plus 1. So let's try understanding what it's trying to tell us. So we have a unique integer a, and it's in the range, and we want to prove that there exists a unique a such that n factorial divides when you raise a to the power of n and add 1 to the result. With that said, let's try out some values of n. So obviously n equals 1 works because that makes a equal to 0 and 1 divides anything. So we're just going to put n equals 1 here at the top because that's kind of a trivial case. For n equals 2, let's see what we need for that. So then 0 is less than or equal to a is less than or equal to is less than 2 factorial, which is 2, which makes a equal to 0 or 1. Then we have 2 divides a plus 1, or a squared plus 1. And if a is 0, then this becomes 0 squared plus 1, which is 1. That's bad, since 2 does not divide 1. And if a is 1, then that becomes 1 squared plus 1, which is 2. And 2 divides 2, so that is good. So n equals 2 works, because then the unique value of a is 1. For n equals 3, we now want 6 to divide a cubed plus 1, where 0 is less than or equal to a is less than 6, since 6 is 3 factorial. And now we can just test values of a out, since there are not that many. And we end up getting 1 cubed plus 1 is 2, which doesn't work. 2 cubed plus 1, which is 9. 3 cubed plus 1, which is 28. 4 cubed plus 1, which is 65. 5 cubed plus 1, which is equal to 126. And then 0 cubed plus 1 over here, which is 1. Out of these, only this guy works here, which gives the value of a to be 5. So n equals 3 works. Could it be that all positive integers n work? Well, let's test n equals 4. Now let's explore n equals 4. So now we want 24 divides a to the 4th plus 1, where 0 is less than or equal to a, which is less than 24. So at this point, we could actually just compute this for all values of a because there are not that many. And if this were in an actual Olympiad, you get the time to do that since there are only 24 values. But a slicker observation is to note that this exponent here is even. So that means that if a works, then n factorial minus a works, because then n factorial minus a to the 4th plus 1. If you expand this out, then you get a bunch of terms equal that have an n factorial term in them, and then this becomes a to the 4th plus 1. So that means that if a equals 12 doesn't work, then there are an even number of solutions, which is bad. And clearly a equals 12 does not work, because that's 12 to the 4th plus 1, and this guy is divisible by 24. So we have just proven that n equals 4 does not work. So what if 1, 2, and 3 are the only ones? This makes us think that n equals 5 might work. So we have 120 divides a to the 5th plus 1, where 0 is between a. 0 is less than or equal to a, which is less than 120. And we could compute the first few values and see if we can attempt to notice a pattern. And if we do that, we don't get anything immediate. We just get 133 and 4, which doesn't really seem good. But if this were if this were good, then that would require that this thing here was a multiple of 5. And by Fermat's little theorem, this thing here is equivalent to a mod 5. So a plus 1 is required to be a multiple of 5, and a is equivalent to 4. mod 5. And in fact, A must be odd because that's the only way it can work. If it's even, then 120 divides an odd number. So this makes A equivalent to 9 mod 10. It ends in the digit 9. And we can try computing things for the first few. Obviously, 9 doesn't work because that makes it not divisible by 3. And then 19 to the 5th plus 1. If we compute that, we get 19 squared is equal to 361, which is equivalent to 1 mod 120. So that makes this guy 19 and therefore 20. With computing this here, this gives us very little hope that there's another value of A which works other than the obvious one, which is A is 119. Why is this obvious, you may ask? Well, it's because when you look at things in terms of modular arithmetic, we end up getting that is negative 1 to the 5th plus 1, which is obviously equivalent to 0 mod 120. So at this point in time, we can just guess that 5 works. So we have these first three numbers here, 2, 3, and 5. And what does this sequence remind you of immediately? Well, this is a number theory problem, so it should make you think of one of the main components of number theory, the prime numbers. So in particular, we conjecture that all n work are n that are prime, as well as that n equals 1 case at the top here. So let's prove it. So we saw what happened with n equals 4 and the pairing argument. So let's see if we can generalize that. So suppose that we have an even integer 2k, because the pairing argument only works when we have an even exponent. So we have 2k factorial divides a to the 2k plus 1. And if a works, then so does 2k factorial minus a, as I argued earlier. And the only one that can't be paired with another is this divided by 2. So 2k factorial divided by 2. But then this to the power of 2k is evidently divisible by 2k factorial, and that makes this not work. So therefore, there are an even number of solutions to this, which makes even n bad. So let's see what happens with odd n. So our first order of action when exploring odd n is to figure out why odd composite numbers don't work. Because we figured out why even composite numbers don't work by the pairing argument, now we just need to show that odd composite numbers do not work. So let's let n be a composite integer. So, and this is our answer. So right now we're assuming that n is composite and odd. And n factorial divides a to the n plus 1. In terms of modular arithmetic, this says that a to the n is equivalent to negative 1 mod n. And since recall that n is odd, or this should be an n factorial, recall that n is odd, so negative 1 to the n is also negative 1. Bringing things to the other side, this gives negative a to the n is equivalent to 1 mod n factorial. And this motivates us to let b equals negative a, so that b to the n is equivalent to 1 mod n factorial. So obviously b equals 1 works, which corresponds to the n factorial minus 1 solution we discussed earlier. And since n is composite and odd, we want to show that there exists some other solution. So let's move everything to the other side, and this becomes b to the n minus 1 is equivalent to 0 mod n factorial, or simply that if we factor it, b minus 1, b to the n minus 1 plus b to the n minus 2 plus all the way to plus b plus 1 is equivalent to 0 mod n factorial. So Ideally, we can get all the factors on one of these terms and leave the other factor for the other term. So let's see if, since n factorial is n times n minus 1 times n minus 2 and so on, and we're looking at n specifically, let's leave out the n for the big term because that seems more controllable. Which means that we leave n minus 1 factorial for this term. And doing so, we want b minus 1 to be a multiple of n factorial, n minus 1 factorial. And this motivates us setting b equals n minus 1 factorial plus 1. So now let's show that this does a trick here, such that for this value of b, this is equal to 0 mod n. So since n is odd and composite, we can write n equals kl, where k and l are both less than n and greater than 1. Then that means that k and l are each inside this n minus 1 factorial thing. So that implies that n divides n minus 1 factorial. So evaluating this guy mod n gives us just this one term remaining, and we get 1 to the n minus 1 plus 1 to the n minus 2, and so on, all the way to 1 plus 1. And there are n of these guys, so the entire thing is divisible by n. So therefore, when b is n minus 1 factorial plus 1, where n is odd and composite, this gives another solution other than n factorial minus 1 for the value of a. And we've just shown that odd composite numbers do not work. Now, all that remains to show is that all odd primes n work. So let's rename our odd prime to p because it's easier to think of primes as p. So then we get p factorial divides a to the p plus 1. And as before, this means that a to the p is equivalent to negative 1 mod p factorial. And since p is odd, this becomes negative 1 to the p, and therefore negative a to the p is equivalent to 1 mod p factorial. Now, in number theory terms, this means that the order of negative a mod p factorial is equal to p, or it's equal to 1. If it's equal to 1, then that means that a is just negative 1, which works. And now we just need to eliminate the case where the order is equal to p. If you did not know what the order of an element inside number theory is, you can go ahead and watch my video on that from last year. I'm going to go ahead and link it inside the description. Anyways, so we want to show that the order cannot be p. And recall that if a number has order p, then or has order suppose k, then k divides the phi of the p factorial, where phi is the Euler-Toshin function, which is a number of terms less than or equal to that number relatively prime to it. So if we can show that p does not divide phi of p factorial, we are set. And this shouldn't be too hard because by definition, this is just p factorial times 1 minus 1 over 2, 1 minus 1 over 3, 1 minus 1 over 5, and then it goes over all prime divisors, so all the way to 1 minus 1 over p. So yeah. And all of these guys in the numerator, because we cancel out a p here, and this becomes now p minus 1, and then that's p minus 1 factorial. All of these guys have prime divisors less than p, which implies that p cannot divide this. So therefore, the order of any element cannot be p, and therefore if negative a to the p is equivalent to 1, then negative a is equivalent to 1 mod p factorial, which gives us our unique solution when n is prime. Therefore, all our answers are n that are prime, as well as our number 1 here. And that solves this IMO shortlist problem N4. Thank you so much for watching this video. Please subscribe if you'd like to see more.